Well, hello everyone, and welcome back to Maths. Last video, we talked about why primes are the atoms of numbers, and we looked at the fundamental theorem of arithmetic, which stated that any positive whole number can be basically broken down into these small prime numbers that basically combine together and create any number. So every single number is made up of primes was the main takeaway. So now we're going to get into practicing the concepts from that video so we can feel comfortable with them moving forward. So I've prepared 5 problems for you here. Please pause the video, give them a shot first, and then we'll work through them together. Alright, so I'm assuming you've done that, so let's go ahead and start. Number 1 says, find the prime factorization of the following numbers. Alright, so the prime factorization was basically we started with a number and we figured out how can we split that number into the prime numbers that make up that number, right? Because the fundamental theorem of arithmetic stated that every single number can be broken down into this unique combination of prime numbers that gives me these numbers. So let's start with 24. So the process was we basically want to chunk off a small prime number every single time. So the smallest prime number we can chunk off from this is 2, right? 24 is an even number, so we can divide it by 2. So if we take 2 out, 2 times what gives me 24? It'll be 2 times 12, right? So 2 is our first prime number in our prime factorization of 24. So now let's keep going here. We have 12. So once again, can we pull out a 2? We sure can, because it's even. So I pull out a 2, and I get the pair 2 and 6, right? Because 2 times 6 gives me 12. So from this, I get that 2 is another factor of 24. And then I can just repeat this again. 6, that's not prime, it's composite, so it can be split up even further. It can be split up into 2 and 3. And 2 is prime, and so is 3. So we get that the prime factorization of 24 has to be 2 times 2 times 2 times 3. And those are all prime numbers, and this is the unique combination of prime numbers that gives us this number 24. And we can also write this in terms of the exponent notation, where we have repeated multiplication here. So we have 2 times itself 3 times. So that's the same thing as 2 cubed times 3. So basically we have the prime number 2 occurring 3 times, and the prime number 3 occurring once in this prime factorization of 24. Alright, so let's go ahead and do 112 now. So 112 is a little bigger, but that's alright. We can just use this factor tree method and it shouldn't be too much of a problem. So can we take 2 out of 112? Well, yeah, we can because it's an even number, right? So 2 times what gives me 112? Well, half of 100 is going to be 50. Half of 12 is going to be 6. So it's going to be 2 and 56 that give me 112. All right, but 56, once again, that's even. So we can pull off a 2, right? Another prime number. And 2 times what gives me 56? Well, it's going to be 2 times 28, right? 2 times 20 is 40, 2 times 8 is 16. So in total, we're going to get 56 when we do 2 times 28. But hey, once again, we got an even number. And in a lot of these prime factorizations, you're going to get a lot of 2's out of it. 2 is the most basic of prime numbers, so it's going to make sense it's going to appear a lot. So 28 can be split up into 2 and 14, right? 2 times 14 is 28. And 14, once again, another even number. So we can pull out a 2 and we can pull out a 7. So 2 is a prime number, right? All these are primes. Is 7 prime? Well, it sure is. You can check, but 7 is prime. It can't be divided by anything other than 1 or itself. So we get that 2, 2, 2, 2, and 7. 2 times 2 times 2 times 2 times 7 is the prime factorization of 112. This is the unique combination of prime numbers which the fundamental theorem of arithmetic guarantees us to have that gives us 112. And writing this in exponent form, we see that we have 2 multiplying by itself 4 times, so we can write that as 2 to the power of 4, right? That's just the condensed way of writing 2 times itself 4 times 7. So this is the prime factorization of 112. All right, let's go on and try with 77. All right, so 77 is odd, so we can't actually pull off a 2. Can we pull off a 3 because that's the next biggest prime? Well, if we add up the digits of 77, we get 7 plus 7, which is 14. But 14 is not a multiple of 3, so neither is 77. So we can't pull out a 3. So what's the next prime number? The next one is going to be 5. But 77 doesn't end in a 5 or a 0, so it can't be divisible by 5 either. So 5 isn't a prime that we can pull out of this. All right, so what's the next prime number? It's going to be 7. So can we pull 7 out of 77? Yeah, if you remember your multiplication tables, we know that 7 times 11 gives me 77, right? So 7 is prime, awesome. What about 11? Can we split 11 up into primes? Well, 11 is actually also prime, right? There is no number other than 1 and 11 that are a factor of 11. So that means the prime factorization of 77 is actually quite small. It's just 7 times 11. And since there's no repeated elements here, there's no like multiple 7s or multiple 11s, we don't have to do the exponent notation like we were up here. Next up, we have 53. Now, we can try a bunch of factors of 53, but if you played around with a bunch of numbers to see if they were prime or not, you're actually going to find that 53 is a prime number. And again, if you don't believe me, you can try a bunch of different factors, but we showed how to do that in a previous video, so 53 is prime. So that means the prime factorization of 53 is just 53 itself, right? We can't split it up any further. 53 is like one of these base atom-like numbers where it is indivisible, it is simply just a prime number. All right, next up we have 80. So 80 is another one. We can start by dividing by 2 because it's even. So we get 2 and 40. And 2 is the prime number we got off of it. 40 is composite, so we can still break that down into 2 again because it's even. 2 and 20, right? 2 times 20 gives me 40. And then what numbers will give me 20? Well, to get 20, we need to take the smallest prime that can go into this, which will be 2 again, because 20 is even. And 2 times what gives me 20? 10, right? So that means 2 and 10 is a factor pair that'll give me 20. And then we just keep going. How about 10? Well, 10 can be split up into 2 times 5, right? And 2 times 5, 2 is a prime number, 5 is a prime number, so we have our prime factorization of 80, which is going to be 2 times 2 times 2 times 2, so we get 2 4 times 5. So this is going to be 2 to the 4th power times 5, 2 to the 4th power because we have 2 multiplying by itself 4 times. So that is the prime factorization of 80. Alright, so I hope those made sense to you. And to get really comfortable with this, for extra practice, you just simply pick a random whole number and see what its prime factorization is. You could do like 118, 3004, right? Like just pick any number you want, and you can find its prime factorization. All right, let's move on to number 2. All right, number 2 asks true or false. So we have 3 statements and we need to determine if they're true or false. The first one says a number can have 2 different prime factorizations. All right, so this is saying that you can basically factor a number and get 2 different collections of prime numbers that when you multiply them will give you the same thing. Now we know with numbers there are different ways to get that number, right? We have like 5 times 4 gives me 20, but we also have 2 times 10 gives me 20, right? These are 2 different combinations of numbers that give me the same thing. However, these aren't 4 and 10 aren't prime numbers, right? So what this is asking is if I look at the prime factorization of a number, will that be unique? And for this, we need to go back to what the Fundamental Theorem of Arithmetic actually states. So if you recall, the Fundamental Theorem of Arithmetic states that for any whole number greater than 1, it can be factored completely into a unique product of prime numbers. So it says a unique product of prime numbers. So unique means that there's only one possible collection of prime numbers that gives me that number. Any other collection of prime numbers is going to give me a different number. All right, so that means A has to be false, because having 2 different prime factorizations would mean that your prime factorization is not unique. All right, let's go into part B. 2 different numbers can have the same prime factorization. So if I take 2 different numbers, so numbers that aren't equal to each other, do you think it's possible for them to have the same prime factorization? Well, let's say I have the prime factorization 2 times 3 times 7, right? These are all prime numbers. This is going to equal some number, right? We can multiply out, but it's going to equal something. And I'm saying that I have number 1, so I have one number here that equals 2 times 3 times 7, but I have another number here that equals 2 times 3 times 7. So if these numbers both equal this prime factorization, there's no way that these numbers can be different. They also have to equal each other, right? Because if this equals this and this equals that, then they have to equal each other. But this is claiming that 2 different numbers, so 2 numbers that aren't equal, can somehow equal the same thing, right? Have the same prime factorization. And that's not true. That's not how equality works. So B also has to be false. All right, and let's look at part C. 1 does not have a prime factorization. All right, so if we look at 1, you'll recall that the only factors of 1 are 1 times 1, right? But 1 isn't a prime number, so that means that since this is the only factorization of 1 and there aren't any primes in it, then 1 doesn't have a prime factorization. And it actually says this right in the Fundamental Theorem of Arithmetic the way I stated it. I said, for any whole number greater than 1, it can be factored completely into a unique product of prime numbers. So greater than 1. That explicitly is excluding 1 because 1 can't be factored into prime numbers. So C is a true statement. All right, so that was question 2. Let's go on to question 3 now. Does 0 obey the fundamental theorem of arithmetic? All right, so the fundamental theorem of arithmetic doesn't say anything about 0. It says it's only true for any numbers greater than 1. So 0 isn't greater than 1, so it doesn't really fall into it. However, can 0 be factored into just prime factors? Well, we know that 0 equals 0 times 3, right? And 3 is a prime number. But the problem is, if you recall from previous videos, 0 is not prime, right? And any factorization that we get of 0 is going to involve 0 times something. So that right there is not a prime number. 0 can never be factored into only prime numbers because 0 itself has to be in the factorization, and 0 is not prime, as we've seen in previous videos. So 0 does not obey the fundamental theorem of arithmetic. All right, we're just breezing through these now. Let's go to number 4. Find a number with 6 different prime factors. Okay, so this one might seem a little more challenging. So 6 different prime factors. So if we look at the ones we did in this one, okay, we saw that they had a bunch of prime factors, but I mean, 6 different ones? We had 2 occur a ton of times, right? But we saw that this one only had a couple different prime factors. This one only had a couple, right? All of these examples I gave actually only had 2 different prime factors. So are we just supposed to like guess and check numbers until we happen upon something that has 6 different prime factors? Well, that would take a very long time. And the way we actually need to go about this is to kind of work backwards a little bit. So the number has 6 different prime factors. So what this means is that it's going to be 6 numbers, 6 prime numbers, all multiplying each other. That's going to give me this number. And these prime numbers all need to be different. But who says that we can't just start by choosing the prime numbers ourselves and figuring out the number? So I'm actually going to do that. So this is what I mean by working backwards. So I'm going to take 6 different prime numbers. So 2, 3, 5, 7, 11, and 13, right? Those are just the first 6 prime numbers. And then I'm going to multiply them out. So we get that 2 times 3, that's 6. 5 times 7, that is 35. And 11 times 13, that one you might not be able to do in your head, so let's go over here and do it. So 3 times 1 is 3, 3 times 1 is 3. Bring out 0 because we're multiplying in the 10 spot now. 1 times 1 is 1, 1 times 1 is 1. So we get 143 is 11 times 13. All right, so this is going to be a really big number. So now we can do 6 times 35. So 35 times 6 is 6 times 5 is 30. 6 times 3 is 18 plus 3 is 21. And we're done. So we get 210. So we have 210 times 143. And once again, we can do this on the side. You could also use a calculator if you want, but I think it's good to do this because, what if your phone's dead or something? It's good to know how to actually calculate this. So we do 3 times 0, that's 0. 3 times 1 is 3. 3 times 2 is 6. All right, now we're in the 10 spot with the 4, so we put a carry for a 0. And we do 4 times 0 is 0. 4 times 1 is 4. 4 times 2 is 8. And now we're in the 100 spot, so we put 2 more zeros here, and we have 1 times 0 is 0. 1 times 1 is 1. 1 times 2 is 2. And then we just add up all these, so we get 0 plus 3. 6 plus 4 is 10, so we put a 0 here and carry a 1 over. 1 plus 8 plus 1 is 10 again, so 0 here, carry another 1 over. And we have 1 plus 2 is 3. So we get 30,030 as being this product here. So since we know already what the prime numbers are, that gives us 30,030, this is a number that has a prime factorization with 6 different prime numbers, or it has 6 different prime factors. All right, so I think that was kind of a fun problem, and you could use this to, find a number with 100 different prime factors. Of course, that would be really massive and big to compute, and you'd probably need a calculator or a computer to do that computation for you, but you can do it is the point, right? All right, so let's go on to number 5. So we want to find a number with a factor tree that looks like this, right here. So circled spots indicate prime factors. All right, so what we basically need is a number where when we factor it, we're going to get a bunch of prime factors here. So what we can do is just start by putting prime numbers in these circled spots. Maybe I'll put 13 here, 3 here, 2 here, and 2 here. So we're basically saying that the prime factorization of this number is 2, 2, 3, and 13. So these are the prime numbers that we got by decomposing the number into primes. So kind of like number 4, we're sort of working backwards here. If this got decomposed into 3 and 13, that means that this number itself had to be 3 times 13, which is 39. And if this here got decomposed into 2 and 39, that means this number here has to be 2 times 39. So what's 2 times 39? Well, that should be 78. You can check me on that, but I think it's 78. And now, our number that we started with, it got decomposed into 2 and 78, so that means it equals 2 times 78. So our answer should be 156, right? So 2 times 78 gives me 156. So if we kind of work forward now, 156, we chunk off a 2, we get 78. 78, we take off a prime number of a 2, and we get 39, right? Because 2 times 39 is 78. And 39, that's a multiple of 3, since 3 plus 9 is 12, which is a multiple of 3. So with that, we see that 3 is a factor of 39, so that's a prime number that we can pull out. And we get that 3 times 13 is 39. These are both prime numbers, so our prime factorization of 156 is 2 times 2 times 3 times 13. So we were basically able to kind of just choose our prime factors from the get-go and see what number actually has that prime factorization. All right, and this of course wasn't the only answer for this. Just like number 4, it wasn't the only answer. I could have chosen any different group of prime factors, right? I could have gone with 3, 7, 11, 23, 29, and 53 or something like that and multiplied those out. I just went with the first ones that came to mind. But here, you could do any prime numbers down here and you just get different numbers. So I encourage you to try that. You could try something like 2, 3, 3, and 5, right? And see, okay, what would I get? Well, 3 and 5, if this number gets decomposed into 3 and 5, that number means that number is 3 times 5, so we get 15. So now we have 3 and 15. If this number got decomposed into 3 and 15, that means we have 3 times 15, or 45 is the number. And then similarly, if the number we started with got decomposed into 2 and 45, then that means that number has to be 90, which is 2 times 45. So there's infinite different possible answers for this just based on the prime numbers you choose. But both of those examples I just did are cases where the factor tree will look like this. All right, well, I hope that helped, and you should be feeling more comfortable with this now. Again, do a bunch of practice problems. If you have any questions, please ask them in the comments. I'll do my best to answer them. But that's going to do it for me today. So have a good one, stay groovy, and I'll see you in that next video.